Hello guys, welcome to In 5 Minutes. In this presentation we are going to see the twisted ring counter, or also called as Johnson counter or Moebius counter. Now there is a very small change, or there is a small difference between the ring counter and the twisted ring counter. Only a small change is there. So let us start with the twisted ring or Johnson counter. So here once again I am going to consider a 3-bit counter. So I have taken the outputs of the flip-flop A, B, C as QA, QB and QC, and 100 is going to be the reset condition. Now why I am going to call it as a twisted ring counter? Why? Because for the each coming clock cycle, so this is the clock cycle first, second, third, the positions are shown here as per the clock cycle. So QA position will be shifted to QB, QB position will be shifted to QC, QC bar is shifted to the position of QA. So that's why it is called as twisted ring. So for the very first case, that is 100 case, that is nothing but our reset position for the counter. After the reset position, for each coming clock pulse, what will happen? QA will move to QB, QB will move to QC, and QC bar, so QC is 0 here, so QC bar will be 1, that will be shifted to the QA. And the next cycle, once again QA will shift to QB, QB will shift to QC, and once again QC is 0, QC bar will go to the next position, so QC will come here. And in the next clock cycle, what will happen? Once again QA will go here, QB will be taking the QC's place. Now in this case QC is 1, so QC bar will be 0, hence the 0 condition is here. And if you see, once again 0 will be moved and the procedure goes on. So let me complete this graph for you. Once again this 0 will move down to P part, 1 here, likewise it will move. So these are the movements. So for your simplification I will make you notes here. So this will be the first movement, this will be the second, and this will be the third movement. So let us see the circuit diagram. So here is the circuit diagram, same as that of what we have used in the ring counter, but there is a small change. Before applying to that change, we need to go to our reset condition, that is 100. So I will connect preset terminal and the clear terminals of the other two, that is B and C flip-flop. And before applying the first clock pulse, since this is a synchronous counter, that's why the clock pulse are given simultaneously to all the 3 flip-flops. And before applying to the first clock pulse, I need to reset it. Why? Because whenever I power on the circuit, I should know what is the previous state of the counter. Okay, and the previous state, that is nothing but the reset state in our case, should be 100. That's why I am connecting the preset terminal of flip-flop A to the clear terminal of other two, and I am going to give a small reset pulse there before applying the first clock edge. And since QC bar is moving down or going back to the QA, what I will do here, I will connect QC bar all the way back to the DA, that is my input of A flip-flop. It will be just delayed since we are using the delay flip-flops. So whatever the input DA is delayed after a clock pulse, and it will be going to out from the QA, and which is connected to DB, and output of B is connected to DC, that is the input of C flip-flop, and hence the cycle completes. So this is the diagram for your circuit diagram for your twisted ring counter or Johnson counter. And here in the downstage, these are the 3 register R, which is the current limiting register for the LEDs, QC, QB and QA. So the LEDs will indicate you the position.